Alright, Lab 5, the last lab for Physics 2212, let's get into it. Alright, so introduction. The idea of the lab is to measure how fast a magnet falls through a metal tube and compare the results to a computational model. The purpose of the lab is to understand Faraday's law and how a metal tube affects the speed at which a magnet falls through it. So they have the system, which is the tube and the magnet, and the surroundings, just everything else. Preview of the results. The average experimental time was 1.098 seconds. The computational time was 1.146 seconds. So the fundamental concepts, you have Faraday's law, Biot-Savart's law, and Newton's second law. I'm not going to go into it too deep, but basically Faraday's law is just the changing magnetic field through a given loop and just the voltage proportional to rate of change of magnetic flux. That's the main law we're kind of focusing on. Then you of course have Biot-Savart's law going back to the previous lab, and Newton's second law going all the way back to the first concepts of physics. So the procedure was fairly simple. You just grabbed the tube, held it above the table, and just dropped the magnet through the tube. Then we just recorded the time at which it entered and at which it exited, and just subtracted them to figure out what the times were for each of the trials, how long basically the magnet took to fall through the tube. We just recorded that a couple of times, and we got our average, which is 1.098 seconds. Then on the left, you have the dimensions of the tube and the properties of the magnet that we dropped through the tube. And then again, just trials 1, 2, 3, 4, and 5, each of the times, and then just the average there at the bottom, which was again 1.098 seconds. So the computational model, basically here we just took their initial conditions, G equals 9.81, the properties of the magnet, and the dimensions of the tube, and then we just set up our initial conditions. And here we have the main forces. We're applying the force of gravity and the force of the induced magnetic field, and then just the net force as the magnet travels through the tube. Basically the big portion of the code. You can kind of see what's happening. Then on the right you have the start and the end. As the magnet falls through, it basically initially falls at a faster rate as the force of gravity is greater. Then it reaches a constant force as the force of gravity and the force of the induced magnetic field just kind of equal each other. So you have that constant force for the majority of the fall. And then again, the gravitational force increases, and the rate at which the magnet falls as well just increases as a result. And you kind of can see that happening there on the two images on the right from start to end. So potential errors. First, our assumptions. Of course, we negated air resistance. The bar magnet behaved as a dipole in our experiment, and we assumed that the only forces acting on the magnet were the magnetic and the gravitational forces. Kind of just disregarded anything else. So yeah, potential assumption. And then potential error, potential friction, and that was just caused by the magnet touching the tube as it falls, just touching the sides of it or something. Then we have the potential inaccuracies of our time measures. We're not robots, so we couldn't exactly, of course, calculate everything. Then potential air resistance, or just how fast we dropped the magnet into the tube. Of course, create different speeds, which again create potential errors. And so our two questions: what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So going back, remember in Ohm's law, an increased induced current would be created from the decreased resistance. Thus, a little typo there, but thus a stronger opposing magnetic yield would be created and a slower drop from the magnet. Then what if holes or slots were cut into the tube? So it's not a perfect tube, right? How would this affect the ring currents in our model? So a weaker opposing magnetic yield would result from the holes, causing the magnet to fall faster. Just basically, since it's not a continuous tube, the induced magnetic force would be weaker. And so yeah, it would cause the gravitational force to be greater, and just cause a greater fall. Alright, and that's all for us. Thank you.